Thank you everyone for joining our series, and we welcome you all to our today's Rising Star Symposium series from Technical Committee on Cognitive Networks Special Interest Group in AI and ML in Security. So who are we? We are right now a group. Our chair is Professor Subha. She's from Stevens Institute of Technology, and we are 3 vice chairs now. I myself, Devasri Roy from UT Arlington, Professor Hanif Rabari from RIT, and Professor Moinul Hussain from George Mason. So we do host, so we have also online LinkedIn presence. Our group is growing large every day. Now we have 588 members. And if you want to be part of our different activities, please can join our group or reach us out. So what we have done so far, we did a few of virtual seminar series. Our series are virtual because so that we can have an overall worldwide presence and interactivity and connectivity. So this seminar series was about some outstanding and established researchers, professors all over the world. It started during the pandemic time, and you can see that we had quite a lot of such seminars at that time. And all these talks are available in our website and our YouTube channel. Okay, so then when I, Moinul, and Hanif, we joined to this our group like last year in 2023, and that's when I actually just got my job as an assistant professor, and that's when we came to an agreement, and we thought of doing a new initiative from our group. And that's when we recommended that how about we do a Rising Star series to give a platform to people like senior PhD students or postdoc to present their job talk or present their research in a job talk manner to a broader audience, mainly targeted to foster more mentorship and employment opportunities as well. Also reachability, we do a lot of advertisement in the LinkedIn so about each of our rising stars, so that it is also reachable to everyone. So basically we urge our rising stars to give a job talk in an interactive way and for 45 minutes. So these are our previous rising stars. We started with CIE. She was from MIT, and then we had different participation all over from different part of the world and also different part of the US. So this is today our rising star Omar is our 9th rising star. So this is just some ground rule for the talk. Please, everyone is muted on entry, and please stay muted. But if you have question, please anytime don't hold out your question, type in the chat so that we have them. And at the end, our moderator will be moderating them at the end of the talk. But we do encourage questions because this is the talk. Our talk is meant to be interactive. So today our rising star is Omar Hashas. He's a PhD candidate in ACE in electrical engineering at Virginia Tech, and his research focuses on 6G, artificial intelligence, digital twins, and agent intelligence. So he had been very prolific in publishing in different places, very prestigious proceedings of IEEE, transactional intelligent vehicles, IEEE networks, and various others, which I didn't have space to write. So thank you, Omar, for being here today, and the floor is all yours. I'll stop sharing. Thank you.
Okay, thank you, Devashi, for the introduction, and thank you for the invitation, along with Moinul and the rest of the team. I'll go ahead and share my screen. I guess you can see my screen now, right?
Yes.
Okay, perfect. So thank you again for inviting me to this Rising Star Symposium. It's a pleasure to be here. And I would like to talk today about some of my recent works. which is basically on digital twins and world models and how they're shaping the next generation of AI, wireless networks, and robotics. So digital twins and world models have catch up recently, and they started having a little bit of hype now, especially after the generative hype, because we saw a little bit the limitations of generative models, how they're applied, which are great, but they still have some limitations. So we're going to see basically how when we combine both technologies, or basically even the fusion of both technologies, can help in addressing these limitations. So first of all, to know how these technologies will be able to bridge into some new generation, we should be able at least to define the current generation that we have. So I'll skip this slide. Thanks to the Bashri for the introduction. So basically, yeah. So if we zoom out a little bit now and we look into the current generation that we have. So if you're into 6G, you're definitely going to see the topics that I'm going to say now, which are on the right. So you've definitely seen papers about terahertz, NTNs, non-terrestrial networks, RISs, reconfigurable surfaces, massive MIMO, ISAC, Open RAN, and whatever applications can come along that scheme. And with those technologies that emerged, or at least starting to emerge now, we can see that the data rates are enhancing the spectral efficiency, reliability, latency, energy efficiency. Everything is going on perfectly well over there, and we're somehow working on another side of AI native networks, which is basically trying to implement the AI into the network itself in order to help even enhance the network capabilities even more. So we want these data rates to become even better, the spectral efficiency to be even better, address more of the limitations, making it more autonomous. And for that, we have different tools that we're implementing to the network, such as the neural networks, generative AI with all the LLMs and diffusion models that we're seeing. We have the semantic communication, which is by itself a new paradigm and it's based on AI. We have even other tools such as neurosymbolic AI. So basically all these AI tools that we're seeing on the other side of the story are helping this network to become so-called more intelligent and be able to become more autonomous and be able to enhance its capabilities. So assuming that we started in 2030 doing all of this together and we reached the end of the road in 2040. So basically we want to now go and reach a new generation. And as we know, a new generation rises basically with a new leap. So the transition from 3G to 4G, we had a leap. From 4G to 5G, we had a leap. From now expectedly from 5G to 6G, we have a leap also. And assuming after 6G or at the end of the road of 6G or somewhere in between, we're going to have a new leap. And we should be able to identify this leap where it is. So now we're still here in 2030, but we should see the end of the road, at least to know where we're going. So we have to ask the question, what do we still need in order to leap into something new? And what are basically the challenges at the end of the road? Probably these can actually help us to know where the sleep is. So possibly as a small teaser. So at the end of the road, we want to reach something which we'll talk about later, which is called AGI native network. So we've moved a little bit away from AI native network into a new type of AI native network, a next generation AI native network with its own type of use cases. And we'll catch up with that during the talk. So basically, we're looking at the limitations. So what are the limitations that we have over here, at least with AI? The limitations with AI are basically that the AI that we're using today relies so much on large data size, and it's not that generalizable. So we can see here that using the AI that we have today, you always have to assume certain conditions which are somehow violated in practice, such as the non-stationarity stationarity assumption, which is violated by non-stationarity of the world. You also have limited interpretability. We have these big models that are being implemented. We can't see anything inside what's happening. Are they safe? Are they not safe? We don't know that. And they're mostly in nature, they are reactive. So you have a bunch of parameters that are just implemented inside these AI, and they begin on calculating and moving on, we can't basically touch it that easily without affecting its goal or its job. So we're always stumbling into a certain type of problems, which are like frequent retraining, and so we always need to update this model. We always need to move on. So that's from an AI native network perspective. So now after we zoomed out a little bit, we're going to zoom in now a little bit to the end of the road where I was showing a little bit earlier. So if you want to look at the end of the road now, and assuming that everything went on perfectly well, and assuming that we reached somehow like the 2040 era. So what we're trying to say here is that we're actually looking for this leap. So is it going to be a new leap in AI or wireless technology, since AI has already been a part of the network and it's doing tremendously different things to the network and it's shaping it in a very nice way. So the question is, what are the limitations now that we really have? And how can we actually move a little bit even more forward? So we can see here that uh, we reached the point where we kind of extensively used the tools that we had, that we used when we were dealing with signal processing, basically, even to be more specific. Uh, so assuming that the road is not going to end, the road that we had on the right side is not going to end. There's still going to be a road over there. But we're going to face a little bit of limitations that are going to be like hurdles for us. We can't push further on that road more so that we can find that leap that we're searching for to jump onto a new generation. So basically, these hurdles are like the Shannon capacity that we have. So basically, we're somehow nearing the Shannon capacity. There are some studies that say that we're reaching around 2 dB below from the Shannon capacity. So which is a good sign that we're doing communication in a very nice way. At the same time, we have a scarcity of spectrum. We have very limited bandwidth. Of course, you're always going to do refarming and always going to change the networks and always going to change the capacities. But basically, we have a limited capacity. We need to deal with this. And other than that, we have problems when dealing with uh, the massive number of antennas that we have. So we're going to reach a practical limit. We can't add any more antennas. We can't add uh, more design features possibly to even enhance even more. So with that, the only way possible to go forward and the only way we see in front of us now is basically to build on AI. But as I said, already AI has its own limitations. So um, and we see now that the kind of AI that is at least going more forward with the AI, it's not the regular AI. We can see here now with LLMs that the big boom that's happening with LLMs is that it's the agentic framework that started to take shape now. And that was due to a couple of cognitive capabilities, such as reasoning and planning. And it started even to become a service now. So I think most of you know like the O series from ChatGPT, where you press and say that I want it to reason, as if it's becoming more intelligent and it's even able to become even better. So if anything, this shows that these capabilities are actually important when you're tackling intelligence, but they're seriously not enough. There are a lot of serious doubts now that these capabilities, they're good, they're a good starting point, but they're also not enough. So basically, we have to ask the question, what do we still need if we really want to build on that other track? And assuming that the first track is going to still have some technologies, but we want to have something like a big step forward. So can we do something with AI over here? So as I said, the reasoning that we have now, that we're seeing, like the chain of thoughts, causal reasoning, all this stuff, by themselves, they're not able to deal with all the problems that we have in the world, because the world is so complex. It's not captured that much in terms of text with LLMs and all this stuff. So it's unable to deal with unforeseen scenarios and reach full generalizability. So give it something from outside its training data for this AI model. It possibly can render something, but it's not going to be 100% perfect. Uh, but at the same time, we know that humans actually know how to deal with this. So if anything, this shows that we're actually missing other abilities other than reasoning and planning in the agentic frameworks that we're actually seeing. So what is this cognitive ability that we're actually trying to search or trying to find in order to do this, to find this breakthrough that we're talking about? So it turns out that at least from one side of the story, this capability is called common sense. So it's basically, we're going to explain it more in detail, but at least initially I can say that it's a common capability for every one of us as humans. And it's the kind of golden capability that you have in order that we use when you're stuck or when you have to deal with a new scenario that you don't know anything about. So, for example, it's like, uh, I don't know, seeing an obstacle for the first time for you, you can identify that it's an obstacle, even though that you don't know all the parameters of it, all the features of it. You never interacted with it, but there are certain features of it that you're 100% sure that it exhibits, that's this obstacle that you're seeing exhibits. And at the same time, you're making sure that you're making sure that what you're implementing or how you're dealing with this new object uh, is good enough. So this is basically, this is our common sense. It's the kind of 2 seconds that you use when you do the so this is kind of the capability that we're trying to search for, and it's missing now in AI. So in order to do that, how can, or basically, how can a wireless network, if you want to do this on a wireless network, how can a wireless network acquire this common sense? So it's basically through something called a world model. So long story short, a world model is a representation of the world that you have around you. You're going to use this representation, which is somehow similar to what we've seen before in model-based RL, but in a different form. So it has a different purpose. And what happens when an AI native network actually acquires this common sense and gets this world model? This is actually what leads to what we saw earlier, which is called, which is the transition towards AGI native networks, artificial general intelligence native networks. Because as we said, this is kind of a common capability to all humans. So there's a level of intelligence that is common to us now. This becomes more as a general feature, and it's able uh, to allow you to deal with this with these unforeseen scenarios, to reach full generalizability. So that's why we're targeting it as a generalizable or artificial general intelligence native network. So so basically, what is common sense? So common sense is an ill-defined concept even in AI because it's very tricky. But we do have pillars of it which we can identify and try to build on top of it, or at least try to capture them all together in a systematic format. So the first pillar is dealing with unforeseen scenarios. It was what we were talking about, and it basically relies on something called horizontal generalizability. So, assuming knowing that I learned how to, I was trained to open a door. If I see a window, can I know how to open it? Which is basically leveraging your common knowledge about opening something to do another task. And that also relies on something else, which is called analogical reasoning. So basically, you have a task A, and it's very much similar to task B. Can I use the skills that I used over here in my other task if I do some analogy between the two things? The third thing is basically, which is very important, it's called intuitive physics. So it's basically the physical principles that we all share about the world, even though we don't express them. So this is a very big topic right now in AI. And it's, if I want to put it down schematically, so it's something like this. So a person, when he's sitting down on a chair and wants to throw um a paper plane towards the basket. I think most of us did that somehow in our life. So to do that, you just throw it, and it most of the time you do you do reach the bucket. So you did that without putting down any math, any calculating, any parameters, any projectile, any physics equation, whatever motion equation that you may have. You just did it and it reached. So this shows that you do have a level of physics that is somehow common to all of us, which we kind of have, but we never expressed. The fourth part is filling in the blanks. So filling in the blanks is a very important is a very important trait of human beings, which is captured through common sense. And it allows you to connect the dots to perform any logical reasoning of events. So simply, I can possibly say 1, 2, 4, 5, 6, 7, 8. You can know what numbers I skipped. This is basically a very important trait of human beings. So what do we have about this common sense? What do we know? What do we have as literature right now? So there's a I think most of you know there's a big AI pioneer. He's called Jan LeCun, which posed down a new architecture that kind of captures this ability in humans. It's basically it's a cognitive architecture. It's a cognitive brain architecture. It's based on different cognitive modules. So these modules are perception, word model, configurator, actor, cost, memory. Uh, and it's also based on sensing, which doesn't appear here. So basically, what's happening here is that we're trying to move towards an architecture that is able to reason and plan and have this common sense about the world. So, but what's happening here is that this architecture still faces a lot of problems. So it's subject to different limiting constraints and challenges, such as the fact that if you want to implement this architecture on the level of a robot or a vehicle or a drone or whatever, the fact that in order to do this, this is based on an ability of prediction. So what we're kind of doing, as I said, a world model is the ability to take in the world and be able to predict what might happen next through some actor module that you have. So basically, as if you're imagining. And this is also a big part of our intelligence, if I must to say that. Imagination is a very big part of our intelligence. So, and it also plays a big role in reasoning and planning. So basically, implementing this architecture on the level of an agent is very hard, because in order to do that, you need to at least have the agents synchronized with each other so that you have the worlds are persistent. Not so. Imagine just having a lot of people just imagining something, and there's a difference in time, in synchronization between the things. It will lead to major chaos. The second thing is that the world models that we have, we're pretty sure that humans share some world models that are somehow common, but we're not sure that we can actually do that on the level of an agent. So you can't just distribute world models to every agent in the world and make sure, I don't know, maybe it has a wrong world model and it will lead to some catastrophe. At the same time, we don't know still how to deal with overlapping worlds, basically in a multi-agent setting, and how things that are common to you and me and everyone, if people are sitting on the same table, how would you act? The table is not for me, it's not for you, we're sharing it. Can I imagine and just, can I do something on my table or not? Do I have the priority to do that or not? That's a different story. And how do these elements that we talked about, the pillars, so the intuitive physics, the analogy, all these pillars, how do they come into this architecture that he proposed? We still don't know that, and it's missing in the big vision. And one of the biggest things is that we still have a mysterious component, which is called a configurator. So the configurator, as you can see here, it's the blue part on top. What it does is that it configures the other modules. So it has kind of a systematic adjustment role. So, and its role is basically to adjust the perception, actor, critic, and word model according to the objective that you have in hand. So basically, with all these limitations, we saw that possibly wireless networks can help in this new vision that we're proposing. So we have here, this is a part from a blueprint that we have for a proposed vision for next generation networks. So you can see here, it resembles a little bit the architecture that we had over here. It looks pretty much the same, but we removed the configurator mechanism. We turned out that if you use this architecture on a wireless network, you do not need this configurator mechanism. And basically, what you can do here is that you can actually allow the network to acquire this common sense. So it would have an upper hand in the intelligence in the world around it. And after you do that, you can actually build on, or basically before that, you build on the capabilities that we had. So all these technologies that I talked about earlier, the ISAC, semantic communication, the representations that we have in semantic communications, all the wireless sensor networks that we have. So all of them converge down to a single vision, which is being able to acquire this common sense to achieve this new vision and to achieve this new leap. But till now, I still didn't talk about the agent itself. I said that the network is going to take in acquire this form of intelligence. Assuming that, I think most of you in 6G know that we also have a new topic, which is called digital twins. So digital twins is something that we have been studying for a while now. And it's basically, it's building these replica of the agents on the network. So it has been used in different contexts. But if we can look here, like when we said we're going to have the world and we're going to do perception. So the perception is basically considers the world and the agents that are inside it. So we're going to take this vehicle and the dog and the human and the building and the tree. Everything's going to be perceived onto the network. The agent itself is perceived as a digital twin. So now, since I have my digital twin and I have that world model, so my digital twin basically means that it's in the world model. The fusion between the two actually will allow me to initiate the role of a digital twin, which is basically to optimize my physical twin in the world. So now what happens is that using this, something that's very known in the digital twin literature is called proactive configurations and optimization. So as a digital twin, you always send optimization parameters to your twin. So doing that, you are able to pass down the common sense that the network was able to handle, or at least to get. You're passing down these abilities down to the agent. So in this case, you have now an architecture on the level of the network that is able to achieve common sense, and the network is able to benefit itself. It did a leap that it was trying to search for. It achieved a new level of intelligence. And at the same time, we're passing this intelligence down to the agent. So we have this agent down on the ground, which is able also to benefit from this type of intelligence. So it's a win-win game. So to make it a little bit more concrete, these are basically two examples over here, which we can use to see just how things are going. So we have the first example. So assuming that you're doing beamforming at the level of base station and you want to send the beam to the vehicle that is moving, and everything's fine as long as you don't have an obstacle. And now we suddenly have an obstacle here. So what happens usually in this case, if you're using just the regular AI that we have today, even with the biggest AI that we have today, is that the signal will be blocked because it's trained on location and all this stuff. It doesn't know that if there's an obstacle, I should change my beam. I should not do that. So using AGI now, the network acquired this level of physics. So it learned what these intuitive physics principles. It's something, so if I want to just name a few of these principles, they're basically the momentum, weight, the collision, object permanence, that things don't disappear. So all of these are basic physical laws that are encompassed in intuitive physics. So now a network can see that I have an obstacle here in front of my vehicle. I know that the beam now is going to be blocked. In this case, what I'm going to do is that I'm going to switch to a new beam. In this case, as if it expressed a higher level of intelligence that was not there in AI native networks. Another example, which is which is basically analogical reasoning. So assume that you have a vehicle on the road and it's moving, and suddenly the vehicle sees a new obstacle in front of it. With the AI that we have today, this vehicle will, if I'm going to borrow the term, it's called hallucinate. If I borrowed it from LLMs, the vehicle will possibly hallucinate or do something that is radical. Using AGI, because of course it wasn't trained on that obstacle before, it wasn't in its training data. So using analogical reasoning and the network can at least identify that this is an obstacle. The agent did not see that before. And the network, and if it bumps it, it will crash. So I should possibly move it around. I should take it to the next lane. So because if I don't do that, of course, it will crash. And the crashing, the collision that I talked about is a part of intuitive physics. So with that, we were able also to solve the problem for the vehicle itself. And this is what I meant, where we have a new level of intelligence, even on the agents or the robots that we're going to see in the world now. So as I said, it's a win-win game. So the question now is basically, if I even want to make it more concrete and I want to make it even more simple, I can even refer to some animation over here. So it somehow looks something like this. So you have an kind of an AI supervisor, which is the network, and you have an AI agent, which is a clumsy Tom from Tom and Jerry. So basically, you know that this agent is going to do a lot of trouble. So what you do is that you kind of give it a command. You come here, you go there, in order to optimize it. It's the same way. It's the same way where it appears here with this animation. So just to present here what digital twins are, just in a small number of words. So basically, what we're trying to do here is to fuse the digital twin inside the world model and predict what will happen at time t+1, t+2, t+n, and use this predicted imagination, which is a form of reasoning and planning, in order to inject it back as configurations to the physical agent. So this is basically, for the sake of brevity, this is what a digital twin is. It optimizes, so it's a digital replica. It optimizes the physical twin, and it does that through analysis, forecasting, and monitoring. And it's based on real-time information update, or basically what we call sensing. And it returns back this optimization parameters or configuration back to the agent. And in order to do that basically in real time, because we know this also has to be in real time or else it won't make sense. What we have to do is that we have to take these digital twin models down to the edge. And as we said, we're fusing them with the world model. So this means that even world models need to be at the edge. So basically, we need to move towards decentralized edge-enabled digital twins and world models. And we kind of address something around that if we want to build now the modules around this architecture. One work here is that we kind of addressed back in 2023, which hits directly on that point, which is assuming that you're going to have these agents on the edge and the world models at the edge. So this was explained in the context of metaverse by that time. But assuming that you can transfer the meaning from metaverse to a digital world model, they're somehow related. So basically, what we see here is that we presented a kind of a new design in order to decentralize the world. So each base station by itself can become can replicate a part of the world. It replicates the physical agents as digital agents or digital twins, and it replicates the rest of the world as a world model. So now we have the physical agent in the physical world, and we have the digital agent in the digital world. So we can see here, if I want to just do that for the sake of brevity and the sake of time, I'm going to skip a little bit here just so that we're not late enough. I'm going to skip a little bit here the math, but what we're basically doing is that we're trying to minimize the latency that we have between synchronizing the agent with its digital twin and the world model with its digital world model. So basically, this sums down into an optimization problem. We're trying to, as I said, we're trying to minimize the total synchronization time of the whole system. We want it all to be synchronized between the physical and the digital world. And of course, we have limitations on the variables, such as the computing resources. And solving this problem is kind of challenging because what we have is that we have sets and we need to divide this world onto base stations. So these are kind of mutually correlated regions. So it's very hard to kind of decompose them in a very independent way. And the distribution of the digital twins and the world, they are also dependent on each other. So in order to solve this problem, we resort to something called optimal transport theory, which is a good mathematical tool, which works on mapping distributions to other distributions within with the least effort, if I want to say, the least effort possible. So basically, what we're searching about here is that our problem it can be posed as an optimal transport theory problem, where we kind of move the distributions that we have for the sensors and all the things that we have in the real world onto the edge servers, which we have, or the base station levels, in order to replicate the whole world. So we're mapping the physical world onto the digital world through the base station. So if I want to skip here these things, so it's basically we're trying to find an optimal transport theory map. So assuming that you found this map here, it turns out to be a semi-discrete optimal transport problem. And we have, we're gonna do an iterative method in order to find the best possible way to distribute this world onto base stations. So this is a part of the results over here. So what we have is that we simulated four base stations. So we have here the S1, 2, 3, and 4. And we have these dots in between, which are the physical agents that we have. So with these physical agents, we have also squares, uh, which represent the world, the physical world that we have around the agents. And assuming that we have a very big, large number of sensors that are deployed, we're able to replicate everything in the world, along with the physical agents that we have. So we can see here that we use something called an SNR-based method in order to allocate these agents and the world onto the base stations. It's centered around this point over here. So the center of the sensing density that we're talking about. So most of the information is being produced around this point over here. So basically, we can see that this results in a uniform association. So which basically does not respect the fact that you have limited resources at the edge servers, and that you should basically distribute the world or sense the world in a non-uniform manner, if I want to say. And at the same time, on the right hand side, we can see that this is our proposed optimal transport algorithm. So we can see that we now have non-uniform associations. We can see here that the regions where we had a lot of sensing, you took in a lot smaller region of the world in order to replicate it. And once you replicated it, you can see here that you actually have these agents that are inside. So you can see most of them are so in the green region, you can see that most of them are actually red. So red means that you have a very high synchronization requirement for this agent. So it's not going to accommodate a lot of agents inside, because it has to accommodate also a large number of world model elements that it also needs to synchronize. So you can see here that we kind of distributed the world onto base stations in a way which respects the resources and still minimizes the latency that we're trying to target, or the synchronization that we're trying to target. This also shows that we were able to achieve this. So if we want to move in forward, so now we have a world, we have the base stations, we kind of replicated the world on the base stations. Now we have to extract the meaningful data from the sensing data. So data by itself is just sensing. We have to extract the meaningful information from inside, and that's called perception. So perception is basically, it's the ability to capture generalizable abstract representations. Because as we said, we have to predict the world, so we have to use it with physics, and at the same time, we have to do analogy with different things. So we need to have the abstract representation, we need to have it generalizable in a certain format. So it's abstract because these representations are abstract because they kind of summarize the real world that we have around us. So you can, it doesn't take in all the features that we have. So it doesn't take it all in details. And that is actually how you predict. You do not predict everything in detail. Nobody can predict 100% how each element is going to change. You predict in a very abstract type of format. And the representation, which means that you're kind of posing it down as a symbol. So you have now kind of an abstract symbol. So how can we actually do that? So we have the sensing data and we want to find these abstract representations. How can we do that? So it's basically through disentangling their semantics. So I'm gonna refer here to a paper from one of my colleagues, which kind of proposed that if you have, let's say, a dog, for example, here, this dog has certain features that are learnable and serious, and other features that are called spurious. So basically, if you capture each dog, you can know that the dog has ears, eyes, a nose, a tail. You can take these as generalizable format, take them to identify a dog, and you have other things around it, like the color of its fur, I don't know, its leash, something like that. So these actually come on top. So when you predict or you deal with abstract representations, you don't rely that much on these things that are these information that are on top. You take more the discrete or possibly the most abstract level of the element that you have. It's just like when someone tells you, draw a car, for example. I assume everyone's going to draw a box with two vehicles down. So this shows that you have an abstract representation of the elements of the world. So the question here now is, how do we actually encode this? So we said that so we kind of identified now. So we're identifying this learnable data. This is what's going to lead to our abstract representation that we're kind of searching for. But how do we actually do that? So we need to find characteristics, basically, because we need to encode. So the characteristics are as follows. So basically, it's generalizability, because we need to maintain a common generalizable form for analogical reasoning. Assuming that I took a symbol of a car, and how can I relate it to a symbol of a truck? I need to make sure that these two symbols actually look similar to each other. At the same time, we need to respect the causality. So we need to make sure that, if you have this feature and you change it, it will change another feature. So we have kind of causal relations between the different features or even between different elements. And at the same time, we need to make sure that it holds the essential characteristics that define this car or this dog or whatever that we have in hand. So this is the big picture of perception here. We're taking, as we said, so it's combining it with sensing. So we're taking in sensing. We're trying to learn the data, trying to see what are the learnable part of the data. Then we're abstracting this learnable part of the data. We're doing some encoding for the semantics of this abstract element that we have now. We're trying to encode it in a way that respects both generalizability and causality while keeping it in a very abstract representation format. So this is also summarizing it. So if we want to move now to the world model itself. So we talked about having a world model over here. We said now what we have is that we have symbols of the world. Now what I want to do is that I want to predict the future, because as I said, this is a way of how you really reason and plan into the future. This is how you reason and plan. So what we want to do is that we want to make sure that these representations are actually fit to do that operation, or basically these abstract representations, they are capable of doing this with physics and all this stuff. So to do that, there's a very nice way, which is based on something called hyperdimensional computing. So it's the ability to draw these vectors in a way that captures all their features in very high dimensional space. And this is basically how we humans represent encodings in our brain. So assuming that I'm going to ask you for a red Tesla, you don't have a representation for a red Tesla in your mind. In your mind, you have a representation for a color, and for a vector that's called color, and a vector that's called red, and a vector that's called car, and a vector that's called Tesla. Once you combine color with red, it becomes the color red. And you've combined the car with Tesla, it becomes a Tesla. And you combine red color with car Tesla, it becomes a red Tesla. So inspired from that, this method comes up with the same way to do computations. So it basically says that each representation in your mind is a combination of different feature vectors, and this is how you actually represent the things. So building on top of that, so we have to say that, okay, so we have to now transform these abstract representations that we got, which were in a symbol space, into a vector space in order to do that. So to do that, we have to refer to something called category theory. So we're moving from a category that's called symbol to a category called vector. So it's from the symbol space to the vector space. And to do that, we have to have certain elements such as the functor, which kind of maps each symbol to what it represents in terms of vectors. And also has other elements such as morphisms, which capture the relations between these different elements that we have. So long story short, hyperdimensional computing relies on something called the mathematics of it, which are basically binding, bundling, and permutation. So binding is basically binding is basically combining the two hyperdimensional vectors together, just like I said, red and color. And bundling is basically connecting red color with car, Tesla, together. And permutation is basically doing some temporal reasoning, changing the order of these features to give in some significance. So this is basically how we build our causal world model in our head. So we have a very hyperdimensional space that represents these elements. Now what we want to do is that we want it to work. We want it to move forward. We want it to predict the future. How is it going to predict the future? To do that, it's not a passive component. It takes in actions. So you imagine that you're going to do something and the world is going to change. Of course, there are other elements in the world that are causal and random effects and other natural evolutions, just as the tree that moves its leaves. We have nothing to do with that, but it moves by itself. So we want to predict now the future. I think I'm a little bit short on time. So I'll try as much as possible to summarize. So basically, to do this, we need to have a certain cognitive ability that's called action planning. So to plan into the future, we have two methodologies. One of them is called intent-driven planning, which also appeared in AI native networks. It's called intent-based networks. And we have objective-driven planning. So basically what we're doing, so the difference between them is that one has an objective, the other doesn't have objective. So assumingly, an example for intent-driven planning would be make sure that my user is achieving the best quality of service, for example. You didn't identify anything. You didn't identify a certain number or a certain objective that you should actually move the network to achieve and say that, oh, now I finished my objective. So this is kind of an open-ended goal. So to do that, you need to rely on also other methodologies that are also inspired from the brain itself. Since we're all dealing here now in a brain kind of style, brain level style methodology. So what we're kind of doing is that we need to relate it to something called integrated information. So it basically, we kind of identify how much information is in our abstract representation. So it's based on something called the effect information of state and the cause information of state. And using that, so using the different integrated information of each abstract representation that we have in the world, each circle that we have over here, each small circle that we have over here, when we combine them all together, we'd have something called integrated information for the world model. So now we know how much information we have about the world. And the more information we have, the more we are able to predict into the future with more fidelity. So assuming that I have a very high level of integrated information, I can predict to n future time steps. And if I have a very low number of, a very low number of, a low amount of integrated information, I could possibly predict 2, 3, 4, 5 maximum time steps ahead. This is for intent-driven planning. The other part is objective-driven planning. So it's based on a different type of planning. It's based on hierarchical abstractions. So what we have over here is that we're gonna tell the network, move, let's say, adjust your power allocation by 5%, become more 5% efficient. So what happens is that the network will have to somehow think, how can I actually do that? And to do that, it has to decompose this big objective into smaller objectives at different abstract levels. So it knows that I have to move from one level to the level where I have to have 95% of my power, which means that I have to actually break it down into optimizing my resource allocation and optimizing my configurations. Then optimizing resource allocations means that I have to optimize my computing, communication, network slicing, whatever can come in there. And also optimizing the configuration means that I have to optimize my pre-coding scheme and RAS phase shifts. So breaking down this scheme until you reach the least abstract layer where you actually transfer the solution to the world. This is how you think about something that you haven't seen before or you planned to achieve that objective. So, but basically till now here, we still didn't plug in the intuitive physics because this is still an open-ended problem. So we still don't know 100% how we can able to achieve this. So we know that we're able to represent these elements in the world in the same way that the brain is able to do them, but we still don't know what is the mechanism that the brain relies on, or what are specifically the forces or the physical elements that the brain relies on in order to change these abstract representations in order to predict the future. So we still have a lot of open problems over here, and this is a big area of research right now. And this is basically just a direct example of what we may also achieve with common sense, but from a different perspective, from something called intuitive psychology, not just intuitive physics. So intuitive psychology is the other part of common sense that I was actually talking about. It's the ability to give. It refers to the ability of a cognitive brain to attribute mental states to others and to oneself. So it's kind of, I know what he says, as if you're saying, I know what the other person is thinking about. So if you want to look at this from a very specific case, which is through semantic communications, we can look at it from a, let's say, a holographic teleportation kind of problem, and say that if I have a network that has common sense and it has the ability to do this theory of mind, I can actually optimize the representation that I am sending to the receiver in order to construct that object that I'm transferring over the network by actually knowing what the knowledge of the receiver is. I'm kind of figuring out what the other side of the link, the receiver, actually has in mind, if I want to say. So this is just a glimpse of what we may benefit from the other part of common sense if the network achieves common sense. So in conclusion, we just want to focus on a couple of things, which is saying here that digital twins are not just simulators. So we just said here, we kind of verified that digital twins have a new role, which is through intelligence and not through just simulation. We should focus more on synchronization and accuracy in replicating the world. We should mainly focus on the fact that even in AI, because mostly this is kind of a more engineering kind of problem, just focusing on latency. So if I want to have a world model that is not accurate or is not synchronized with my physical world, it means no sense, and we are not able to achieve what we are intending to. At the same time, we need to focus more on distributed architectures. So we're seeing here that we cannot capture the world all in a single place. We need to have this world kind of distributed over all the base stations that we have, over all the network resources in your home, outside your home, your router, your base station, whatever possible access point that we can have. We need to have a computing infrastructure near that access point in order to help us replicate and to harness this type of intelligence. And we need to focus more on the fact that cognition or cognitive systems do not necessarily need to be centralized in one place. It rhymes very much with the fact that we need to have distributed architectures. But we need to say that intelligence is also compiled. It can be compiled on top of each other, and it doesn't need to be confined, let's say, in a certain robot or agent. And I think by that, I just want to acknowledge my supervisor and collaborators for the great work that they're helping us with. And thank you, and be ready to accept any questions. I hope I didn't take too much time.
That's fine, Omar. Thank you for the nice presentation.
Thank
So
you.
I already see that there is a question in the chat from Kriti. Thank you for the presentation. As a beginner in this digital field, I want to ask following questions. How do you protect sensitive data shared between physical and digital platform? How well does the digital twin integrate with existing systems, kind of compatible with existing systems standards? So
Okay.
first question is about, I think, more about
Protection.
privacy.
Yeah.
The second one is about compatibility.
Yeah, so these are great questions, actually. So basically, protection. So we're kind of considering that we're kind of not going inside sensitive data. So basically, we're kind of considering that the same data that we have today and the same methodologies that we have today in dealing with the security of the data still are still viable in what we're targeting for this type of generation. So basically, the same kind of encryptions, the same kind of things, the same kind of data that you're capturing, whatever we have, because as we said, we're kind of building on what we have. We kind of build on semantic communications, build on digital twins, build on world models, built on ISAC, integrated sensing and communication. So the technologies are already there, and the people that their main focus is there on these technologies, whatever they implemented for trust, if I want to say for trust, for the users to trust in sharing their sensitive data, it should still apply over here. I think the second question was compatibility, right, with standards?
Yes.
Yeah. So basically, I'm sure that there's still not standards. So there are no standards, I think, for digital twins, for example, still yet. We tried to push a little bit earlier on standards or open platforms for digital twins, considering that we have different companies that need to implement their digital twins on the network. But I think that still needs a little bit more time because that needs to build more on the fact that we have APIs now on the network, and more developers are able to come into the network and program and do this programmability of the network, so able to use the network as a service. So basically, it depends on what's going to happen with 6G. So if it's 6G, if technologies get standardized, I think we should be all in a safe place. If the majority of these technologies don't get standardized, there's a big trouble. And we're going to see by 2040 what happens. But at least we should be able to push towards a certain area, because we should identify that there's a possibility or there's a potential at the end of the road that if we really want to reach that point, these are the technologies that we should build on.
Thank you. For the rest of the audience, if you have a question, you can either post or you can unmute yourself and ask directly. So while waiting, maybe I can ask one question. So a lot of fundamental problems that you are trying to address has similarities with other problems that we are facing, like for example in large language models or some other places, right? So what are the differences or similarity for wireless than what we have experienced in these other domains?
Okay, so basically, if I want to specifically talk about wireless with large language models, so the thing is that we're kind of we're an important technology sector that has its own certain characteristics which apply to it and possibly don't apply to many different fields. So basically, we're a society that always has to deal with non-stationary distributions, out of distributions, generalization, all these abilities. These are really the things that we're concerned about when we're dealing with the network, because a network, you cannot apply it in a closed scenario. It just doesn't work. It's implemented in the world. So that's the first, I think, the barrier, if I want to say, the first barrier that you have to achieve. So what happened with large language models is that they showed a lot of intelligent abilities. So we weren't able to, I think it was still 2022 when they emerged. So when they emerged, everyone thought that this is it. We just found a solution. Of course, this needs a lot of research, a lot of experiments, a lot of researchers working on these. But it turned out that what applies to text basically does not apply to the real world, because I can put it in a very simple way. If what applies to text applies to the real world, you wouldn't have your driver's exam. You wouldn't have a part that is actually written and another part which is behind the wheel. So basically what applies here, it's very good. You can use it as a knowledge base for you, and it also affects, and you can refer to it, it affects how you actually deal with the world. And it's a good area of knowledge. But it turned out that the way we actually harness the knowledge, we get our knowledge, is through sensing, through interaction, through experiences. And it's much, much more rich than just piling up static data sets. So I think it's somehow clear now for any person with an engineering perspective. He can see that at the end of the road, that what we're trying to do is that we're trying to make these data sets more and more bigger and bigger. I would say that it did do a lot of improvements. It did help us in different ways, and it affected possibly every field, every sector on the face of this earth. But especially for the wireless network, it still needs to do more. It's better, of course, than the regular neural networks or the autoencoders that we used to do and all this stuff. Of course, it's better. It does have a level of generalizability. It does express a level of reasoning. It does express a level of planning. But since we have these, we're in direct interaction with the world, we cannot just camouflage the bigger problem that we have.
All right.
And that's why we kind of need these new architectures.
Yes. Yeah. Thank you. So I see another question in the chat from Sarah. As someone not really in the field, I'm curious, how do you train the model on psychological and behavioral characteristics? Do you work with experts in those fields, or do you rely in human interaction or something else entirely?
We didn't train the model on anything yet.
Yeah.
Yeah, this is just the vision of how things we may do. I think the only experiment that I showed was the optimal transport theory one. It was a different story. It's just sensing data and communication with the network.
Okay. So I don't see any more questions. Maybe in the interest of time, we can take one more question if there is one. Okay, I don't see any more questions. Thank you, Omar, for your presentation, and thank you for coming here and accepting our invitation. So we look forward to seeing you again.
Thank you. And thank you for the invitation and for hosting me.
All right, sure.
Thank you.
Yeah, goodbye, everyone.